Welcome. Please turn to section 3.4 of the required written modules. By the end of the lesson, you will be expected to recognize characteristics of polynomial functions, use factoring to find zeros, identify the multiplicities of roots, graph polynomial functions, and use the intermediate value theorem. Let's start by identifying polynomial functions. A polynomial function is smooth and continuous. Only two of the four graphs above are polynomial functions. Let's label these a 1, 2, 3, and 4. Which of these functions are smooth and continuous? Let's look at number 1. Number 1 is smooth and continuous. Hence, it is a polynomial function. Let's look at number 2. Well, number 2 is continuous. Notice if we were sketching it, we could sketch this whole function without lifting our pencil from the paper. But it's not smooth. If you notice here, this is not smooth. It's a sharp corner, and we don't want sharp corners. So number 2 is continuous, but not smooth. So it is not a polynomial. Let's look at number 3. Number 3, we can definitely sketch it without lifting our pencil. There are no sharp corners, so it is smooth. So number 3 is smooth and continuous. So it must be a polynomial function. What about number 4? If we were to start sketching this out, we have to lift our pencil and jump to keep sketching it. So it is not continuous. Since it is smooth but not continuous, it is not a polynomial. All right, let's look at example 1. Example 1, finding the x-intercepts of a polynomial functions. Find the x-intercepts of f of x equals x cubed minus x squared minus 4x plus 4 by factoring. So let's start off with writing out x cubed minus x squared minus 4x plus 4 equals 0. And remember, the x-intercepts are found when our y values, that is our f of x, is equal to 0. So we set the whole function equal to 0. Now we can factor by grouping this group and this group. This first group has an x squared in common. So we have x squared, and we are left with x minus 1. We have just undone the distributive property. If we multiply this out, we'd end up with an x cubed minus x squared. Let's do the same thing to the second group. If we factor out a negative 4, which they both have in common, we are left with x minus 1. Now we have this one group or term and this second term, and they each have a factor of x minus 1. So we can factor the x minus 1 out, and we're left with x squared minus 4 equals 0. X squared minus 4 is a special type of polynomial. You should recognize it from algebra. If you don't, I would spend some time reviewing. I have mentioned this before, but this is a difference of squares. So please take a moment and search for that online. If you don't, remember what a difference of squares is. So let's continue. We're left with x minus 1 times x minus 2 times x plus 2 equals 0. So I have x minus 1 equals 0, x minus 2 equals 0, and x plus 2 equals 0. This first equation gives me the solution of x equals 1. Then I have x equals 2 and x equals negative 2. So my x-intercepts are 1, 0, 2, 0, and negative 2, 0. Next, let's discuss identifying zeros and their multiplicities. The number of times a given factor appears in the factored form of a polynomial equation is called the multiplicity. If a polynomial contains a factor of the form x minus h to the p power, then x minus h has a multiplicity of p. Furthermore, the graph of a polynomial function will touch the x-axis at zeros with even multiplicities. The graph of a polynomial will cross the x-axis at zeros with odd multiplicities. So if we have an even zero or even multiplicity, and this will be the part of the graph that touches right here. So this one would be even. It's just touching the x-axis. If we have an odd multiplicity, we do have a couple different cases I want to point out. If p equals 1, then our polynomial will cross the x-axis like a line. So here, this should be like a straight line. If p is greater than 1, so that means it's equal to 3, 5, 7, etc., it'll look, so if this is our polynomial, it'll look more like a cubic graph. So if you remember, the graph of x cubed is kind of curved here where it touches the x-axis, and so is this graph in this case. Finally, one last thing to note, the sum of the multiplicities is equal to the degree of the polynomial. With that, turn to page 2 of section 3.4. So the top of the next page of section 3.4. So we can begin to review example 2. Example 2, identifying the zeros and their multiplicities. Use the graph below to identify the zeros of the function as well as the multiplicity of each. Then write a formula for this polynomial function. So let's say this is our graph of f of x, and it's going off infinitely in either direction. Of course, here is our y-axis, and here is our x-axis. Let's mark off some key points here. Where does this cross the x-axis? I see it here, here, and here. Now, what are the multiplicities of these zeros? If you notice, this almost looks like the graph of a cubed, well, of negative x cubed. And this here crosses as a straight line. And this one here only touches the x-axis. So it's safe to say that we have a multiplicity of 3 here, a multiplicity of 1 here, and a multiplicity of 2 here. If we add these up, 3 plus 1 plus 2, we have 6, so this will be a 6th-degree polynomial. Now let's write out our function it's going to look something like f of x equals some constant a times x plus 3 cubed times x plus 1 times x minus 2 squared. Now, let's review why this looks this way. If this is the solution, x equals -3. If we add 3 to both sides, we know x plus 3 equals 0. So that is the factor of our polynomial. If we have x equals -1, this becomes x plus 1 equals 0. That's our other factor. And lastly, since we have x equals 2, this becomes the term x minus 2 equals 0. So our three factors are x plus 3 with a multiplicity of 3. So I write out x plus 3 cubed, x plus 1 with a multiplicity of 1, that's here, and x minus 2 with a multiplicity of 2. Now we have to figure out what this a is. So let's find another point that we're given on the graph. For this point, I would look up along the y-axis right here. This is our y-intercept. And the ordered pair here is 0, 11. That tells me that f of 0 equals 11. Let's use that to our advantage. That f of 0 equals a times 0 plus 3 cubed times 0 plus 1 times 0 minus 2 squared equals 11. So I know that a times 3 cubed times 1 times -2 squared equals 11. This becomes 27 times 4a equals 11. Pull out a calculator. If you notice, 27 times 4 is 108. And that equals 11. So a, finally, if we divide both sides by 108, we end up with a equals 11 over 108. So our final polynomial is 11 over 108 times x plus 3 cubed times x plus 1 times x minus 2 squared. Let's look at example 3. Example 3. Sketching the graph of polynomial functions. Sketch a graph of f of x equals 2. Sketch a graph of f of x equals 2 times x minus 4 times x plus 2 cubed. Let's start by finding our x-intercepts. So we want to solve 2 times x minus 4 times x plus 2 cubed equals 0. This means x minus 4 equals 0 and x plus 2 equals 0. Now what happened to this leading to? If we divide both sides by 2, we end up with just x minus 4 times x plus 2 cubed. And what about the cubed? If this were cubed and we took the cube root of both sides, the cube root of 0 would just be 0. So you just need to focus on the factors themselves. This solution here is x equals 4, and this one here is x equals -2. So those are my x-intercepts. What about my y-intercept? That's equal to 2 times -4 times 8, or -8 times 8, which is just -64. So let's start on our sketch. So let's go ahead and sketch out our zeros, or our x-intercepts. This is at 4, 0, and -2, 0. And our y-intercept is at 0, -64. So these are the 3 points we need to sketch out. Here is 4, 0. Here is -2, 0. And here we are at negative 64. Now, what is the end behavior of this graph? Well, the degree of this polynomial is found with this x and this x. This is going to be to the power of 1, and this is going to be cubed. So this will come out to x to the 4th because I have an x here and an x cubed. So this is a 4th degree polynomial. This tells me that it should go off in this direction and this direction. So as we approach positive infinity on the x-axis, we'll approach positive infinity on the y-axis. As we approach negative infinity on the x-axis, we'll approach positive infinity on the y-axis. Now, what about our intercepts? This intercept has a degree of 1, so it should cross as a straight line. This one has a degree of 3, so it should look almost like the graph of something cubed. And then we know we want it to cross here at our y-intercept. Now let's use technology to finish our graph. So take a moment and open up your graphing calculator. As you can see, my graphing calculator is out now. Let's go to our y equals. Here is the function we want to type in. 2, then parentheses, x minus 4, close our parentheses. Then we have x plus 2, and we're going to use this symbol here to get to the exponent and put a 3 there to cube it. Now let's change our window. Our minimum can go from negative 5 on the x to positive 5 on the x-axis. Leave it scaled by 1. Our minimum y, let's go to say negative 350. And let's go up as high as 150. And let's scale this by 64. And now graph. There we are. That gave us a really nice picture of what our graph looks like. Let's use the calculator to find what this minimum value is. So you're going to hit second and the trace button to get to the calc menu. Go here to number 3, minimum. And now let's go ahead and use our arrows to find the leftmost or left side of this minimum here. Let's move over to the right of this minimum. And now let's give it a guess right here somewhere. And looks like our minimum is located at, so let's write this out, our min is located at negative 2.5, oh excuse me, positive 2.5, then negative 273.75. 0.375. That looks about right. There is our minimum, and we can use that to help finish our sketch. So right here at about 2.5, we have negative 273.5, which is here. Now we can connect these dots. There we are. And I'm even going to clean this up a little bit. Next, let's look at the intermediate value theorem. Let f be a polynomial function. The intermediate value theorem states that if f of a and f of b have opposite signs, that is, one is positive and one is negative, then there exists at least one value c between a and b for which f of c equals 0. So if we have some function here on our Cartesian plane, and it's a polynomial, and let's say my function looks like this. If a is here and b is here, notice that f of a is greater than 0 and f of b is less than 0. Because f of a would be here, and f of b would be here. Because of this, I have to cross the x-axis. Since polynomials are smooth and continuous, there's no way I can get from the positive side to the negative side without crossing the x-axis, and this here is the point C, and f of c equals 0. So this is what the intermediate value theorem tells us and looks like. Let's turn now to the last page of the section 3.4 notes. We're going to use the intermediate value theorem for an example and then discuss global extrema and do a real-life application. Example 4, proving real zeros exist with the intermediate value theorem. Show that the function f of x equals negative 4x to the fifth plus 2x squared plus 1 has at least one real zero between x equals 0 and x equals 1. So what we need to do is evaluate our function for x equals 0 and x equals 1, and then check the signs. Is one of them positive? Is one of them negative? So let's start with f of 0. This equals to negative 4 times 0 to the fifth power plus 2 times 0 squared plus 1. This term and this term vanish since we have them multiplied each to 0. Their product is 0, and these two sums of 0 plus 0 are just 0. So we end up with f of 0 equals 1. Notice that f of 0 is positive 1, so it must be greater than 0. Now let's take a look at f of 1. This becomes negative 4 times 1 to the fifth plus 2 times 1 squared plus 1. So we have f of 1 equals negative 4 plus 2 plus 1. Negative 4 plus 2 is negative 2 plus 1 is negative 1. So this means f of 1 is less than 0. So let's draw a quick rough sketch. So we know our function f at 0 is up here at 1. So here's 1, here's negative 1. So at 0, I know it's 1. And at x equals, say, 1, I know we're at negative 1. That means my continuous function somewhere between these 2 points has to cross the x-axis. I don't know where that'll be. I don't know what this will look like. I just know it's somewhere here. I'm going to cross the x-axis, and this is the point C that exists based on intermediate value theorem. So let's write up a more formal conclusion. Since f of 0 is greater than 0 and f of 1 is less than 0, by intermediate value theorem, often abbreviated IVT, there must exist some value of x equal to c such that f of c equals 0. Next, let's discuss global extrema. Global extrema. A global maximum or global minimum is the output value at the highest or lowest point of the function. If a function has a global maximum at a, then f evaluated at a is greater than or equal to every single value of x in the function. So that is f evaluated at every single x within our domain. If a function has a global minimum at a, then f of a is less than or equal to f evaluated at every x within its domain. Let's look at example 5. Example 5, real-world applications. Squares of size x inches are cut out of each corner of a rectangular sheet of cardboard that measures 16 inches by 10 inches. Then the cut corners are folded up to create an open box. Express the volume of the box as a function in terms of x. Let's start with our sketch. And I will say a problem like this is vitally important that you make a sketch to help you understand what is going on. So there is our rectangular sheet of cardboard. This here is 16 inches, so this must be 16 inches. Here is 10 inches, so this must be 10 inches. And we're going to cut out corners that measure x by x. So both of these measure x by x. So that is what our box looks like with the cut corners. What do I have in terms of measurements now? So what does this segment here measure? And what does this segment here measure? Well, I know for the longer segment, I have 16 total, and I'm going to subtract an x and then subtract another x. So this length here is 16 minus 2x inches. This one here is also 16 minus 2x inches. Now for the vertical segments, again, I have 10 inches total, and I subtract this x and this x. So this here measures 10 minus 2x inches, and here I have 10 minus 2x inches. Let's see what this would look like as a box. So if I were to fold this up into a box, I'd have my long side here. I'd have the width here. And then of course you'd have your heights that measure x inches. There's what our box would look like. And let's label everything. This here is 16 minus 2x. Here we have 10 minus 2x. And then of course our height is x. And the colors do correspond to what you see up here. So these purple ones all measure 16 minus 2x. The green ones all measure 10 minus 2x. And these black lines all measure x. Let's recall from algebra, the volume of a rectangular box can be expressed as base times height times width. So in this case, we want to express the volume of a box as a function in terms of x. So we want the volume of x to equal v of x to equal some function of x that relates the base, the width, and the height. So let's take a look here. My base is here, 16 minus 2x. This I would say is a good width, and here's my height. So my expression becomes 16 minus 2x times 10 minus 2x times x, which can just be written as, please take a moment here and pause the video to multiply this all out. Now that you've paused the video and worked this out, verify that your final expression looks like mine. This can be written as 4x cubed minus 52x squared plus 160x. So the volume of the box can be expressed as a function of x as follows. So v of x equals 4x cubed minus 52x squared plus 160x. And this concludes the video for section 3.4.